As we prepare to discuss causal graphical models in more detail, we're going to need to use some terminology and ideas from probability. These ideas will be discussed in this video. The first idea is that of random variables. We refer to variables as quantities or characteristics that we measure on our units of observation. These are things like age, BMI, or smoking status when we collect data on people. The word random and the term random variable refers to the idea that for a randomly selected individual in our population, the value of the age, BMI, and smoking status variables will be random, hence the term random variable. We're often interested in the probability that a random variable takes a given value. For example, we may want to know the probability that a random person from the population is age 40. When a random variable takes a certain value, this is referred to as an event. Here, the event is age equals 40. We denote the probability of this event as P of age equal to 40. In situations where we refer to generic unnamed random variables, we use capital letters, and we refer to the values taken by those random variables with the corresponding lowercase letter. A random variable x can take on a certain set of values, and the set of probabilities corresponding to these values is the probability distribution of x. In other words, probability distributions describe how often different values of x tend to occur. A probability distribution for an age random variable might look like this, where the height of the density indicates that younger ages are more likely to be observed than older ages. A probability distribution for smoking status might look like this, where the height of the bars indicate the probability of not being a regular smoker and being a regular smoker. Another important concept is that of conditional probability. When we describe probabilities of events without taking into account any additional information, this is called an unconditional or a marginal probability. For example, the probability that a randomly selected person from the US has lung cancer is 1 in 1,000, and this is a marginal probability. We can also describe probabilities of events in the presence of additional information about the occurrence of other events. The probability that an individual has lung cancer, given the additional information that they smoke regularly, is called the conditional probability of lung cancer given smoking status. And this conditional probability is 15 in 1,000, much higher than the marginal probability of 1 in 1,000. Conditional probabilities are notated with a vertical bar that can be read as the word given. The information to the left of the bar is the event that we're interested in measuring the probability of, here having lung cancer. And the information to the right of the bar is the given information, here being a regular smoker. A way to view conditioning is the filtering of data down to the cases where variables take certain values. In this conditional probability, we effectively filter the US population to only the regular smokers, and we see that among these regular smokers, 15 in 1,000 have lung cancer. Related to the idea of conditional probability is the concept of independence. Two events A and B are independent if the probability of A given B is just equal to the probability of A. And because independence behaves symmetrically, the probability of B given A is just equal to the probability of B. This means that knowledge of B occurring has no bearing on the chance that A happens. Another way to put this is that knowledge of B does not help us better predict if A will happen. Similarly, knowledge of A happening has no bearing on the chance that B happens. Knowledge of A does not help us better predict whether B happens. If these equalities do not hold, we say that events A and B are dependent. Using the lung cancer example, recall that the chance that a random person has lung cancer is 1 in 1,000, a marginal probability. We saw that the chance of lung cancer conditional on being a regular smoker, that is the chance of lung cancer among regular smokers, was quite different. It was 15 in 1,000. The fact that these two probabilities are different tells us that the events having lung cancer and being a regular smoker are dependent. Knowledge that someone is a regular smoker does change the marginal probability that they have lung cancer. It increases that chance. So this was an example of dependence. What about an example of independence? Let's look at the chance of lung cancer conditional on owning a blue shirt. That is the chance of lung cancer among those who own blue shirts. This conditional probability is 1 in 1,000, the same as the marginal probability of lung cancer. In other words, knowing that someone owns a blue shirt does not change the chance that they have lung cancer. It's still 1 in 1,000. So, knowing that someone owns a blue shirt does not help us better predict if they have lung cancer. So, these two events are independent. Just like events can be independent or dependent, random variables can as well. Two random variables, x and y, are independent if the probability that x takes the value little x, given that y takes the value little y, is exactly the same as the marginal probability that x takes the value little x. And because of the symmetry of independence, the same equality must hold for y given x. And these equalities must be true for all values that x and y can take. If these equalities don't hold for at least one pair of values for x and y, then the random variables are dependent. Just as for independence of events, the independence of random variables tells us that knowing the value of one random variable does not help us better predict the value of the second one. And dependence of random variables tells us that knowing the value of one variable does help us better predict the value of the second one. So for example, the random variables height and liking chocolate are independent. The probability that a random person is a certain height does not change once I know their chocolate preferences. And symmetrically, the probability that someone does or does not like chocolate does not change once I know their height. The random variables height and weight, on the other hand, are dependent. The probability that a random person is a certain height does change at least a little bit once I know their weight. And symmetrically, the probability that someone is of a certain weight does change at least a little bit once I know their height. So the independence of events and random variables that we've just talked about is known as unconditional or marginal independence, because we have not considered independence in the context of information on a third event or a third random variable. At this point, it's useful to clarify some terminology related to independence. When two random variables x and y are independent, we can equivalently say that they are unassociated or uncorrelated. When x and y are dependent, we can equivalently say that they are associated or correlated. We've talked about both marginal and conditional probabilities, and we've discussed unconditional or marginal independence. We can also talk about conditional independence. Because we'll primarily deal with independence of random variables, we'll focus on defining conditional independence of random variables, but similar ideas hold for events as well. Random variables x and y are conditionally independent given another variable z if x and y are marginally independent within all possible values of z. This is best illustrated with an example. The variables of shoe size and reading ability are marginally dependent variables. They're dependent because knowing that someone has extremely tiny feet tells me that they're a child and thus have lower reading ability. Similarly, knowing reading ability allows me to better predict shoe size. Although shoe size and reading ability are marginally dependent, they become conditionally independent given age. Remember that a useful way to think about conditioning is to think about filtering data down to cases where variables take certain values. Once I measure age, I can form groups where all individuals are a fixed age, that is, filtering by age. Within all of these age groups, there is no longer any dependence between shoe size and reading ability. This is what it means for shoe size and reading ability to be conditionally independent given age. Let's look at another example of conditional independence. Say that we measure ice cream sales and the number of forest fires in a month. These variables are marginally dependent. Knowing that a month had a high level of ice cream sales probably means that the temperature was high that month, and forest fires tend to occur at higher temperatures. Although ice cream sales and forest fires are marginally dependent, they become conditionally independent given temperature. When I look at months with a fixed average temperature, there's no longer any dependence between ice cream sales and the number of forest fires. All right, we've seen marginal independence and dependence, and we've seen conditional independence. Is there a concept of conditional dependence? Yes, there is. Two variables x and y are conditionally dependent given z if they are marginally dependent within at least one value of z. Another way to put this is that if we look at the subgroups formed by filtering on z, x and y are dependent in at least one of these subgroups. Let's look at an example. The variables musical talent and being the child of a veteran are marginally independent. Knowing the value of one does not help us better predict the value of the other. But let's say that there's a scholarship that a student can get if they meet at least one of those two conditions, if they have musical talent and are the child of a veteran, or both. It turns out that if we condition on the scholarship variable, musical talent and being the child of a veteran become conditionally dependent given the scholarship variable. This means that within at least one of the subgroups defined by the scholarship variable, winners, non-winners, or both of them, the musical talent and child of veteran variables are dependent. It turns out that the dependence happens within scholarship winners. Let's look at a numerical example to show this. We have data here on 8 students. For each of the 4 combinations of musical talent and being a veteran's child, there are 2 students. Let's first verify that musical talent and being a veteran's child are marginally independent. That is, let's check that the chance of musical talent and lack of don't change if we know whether or not the student's parent is a veteran. Tabulating the no's and yeses in the musical talent column allows us to compute the marginal probabilities. 4 out of 8 students do not have musical talent and 4 out of 8 do. These marginal probabilities are both 1/2. Will these probabilities change when we filter to children of veterans or to children of non-veterans? Within children of veterans, 2 out of 4 students do not have musical talent and 2 out of 4 do. Within children of non-veterans, 2 out of 4 students do not have musical talent and 2 out of 4 do. The marginal and conditional probabilities are all 1/2. This means that knowing information about parents' veteran status did not change the chance that children possessed or did not possess musical talent. These 2 variables are independent, marginally. Knowing the value of one did not help us better predict the other. But now let's condition on scholarship winners. Within this group, the chance of no musical talent and musical talent are 2 out of 6, or 33%, and 4 out of 6, or 67%, respectively. Do these chances change once we know the veteran status of the parent? We'll see momentarily that the answer is yes. This means that there is dependence between musical talent and being a child of a veteran once we condition on the scholarship variable. So in this subgroup of scholarship winners, within children of veterans, 2 out of 4 students do not have musical talent and 2 out of 4 do. So both conditional probabilities are 50%. Neither of the original probabilities were 50%. So the original chances of musical talent and lack of did change once we knew the parents were veterans. Let's also see if the original chances of musical talent also change once we know that the parents are not veterans. In this subgroup of scholarship winners, within children of non-veterans, 0 out of 2 students do not have musical talent and 2 out of 2 do. Again, these conditional probabilities, are different from the original ones. This change implies dependence. In this subgroup of scholarship winners, knowing that the parent is not a veteran does help us better predict musical talent. So there were a lot of calculations in this example, but let's develop some intuition for this. Note that among these scholarship winners, knowing that a student is not the child of a veteran necessarily means that they must have musical talent. The probability is 1. Otherwise, they wouldn't have won the scholarship. So, conditioning on scholarship creates a dependence between these variables, even though this dependence is not present in the general population. The independence concepts in this video will be crucial for us, so let's review what they mean in conceptual terms. We are in general going to be interested in two random variables, x and y, and they're usually going to denote a potential cause and some outcome of interest. So these variables are marginally independent if in the whole population, not in subgroups, knowing the value of x does not help us predict the value of y, and vice versa. These variables are marginally dependent if in this whole population, not in subgroups, knowing the value of x does help us predict the value of y, and vice versa. X and y are conditionally independent given another set of variables, z1 through zn, if within all subgroups formed by these z variables, knowing the value of x does not help us predict the value of y. X and y are conditionally dependent given another set of variables, z1 through zn, if within at least one of the subgroups formed by these z variables, knowing the value of x does help us predict the value of y. Okay, so what is the connection between these probability ideas and causal inference? The ideas we've discussed here pertain to relationships between variables that can be checked from data. These ideas will be our bridge from the qualitative cause and effect relationships embodied in causal diagrams to statistical properties of data. It turns out that causal graphs that encode essential expert knowledge are in fact statistical models in disguise. They graphically show relationships between random variables. We will see that structures within causal graphs imply marginal and conditional independence and dependence between variables. In other words, causal graphs will be able to tell us how variables are associated, and the probability ideas discussed here give us the language for describing different types of association or lack of association, namely marginal and conditional association and lack of association. This will help us in two ways. First, the associations, aka dependencies that we see in data, can be expressed as a combination of causal and non-causal effects. If we can remove the non-causal parts of associations, we can perhaps isolate the causal effect, at least the part of the association that is purely causal. We'll be able to do this by using the concept of conditional independence. Second, we'll be able to use statistical methods to check whether our data are consistent with the expert knowledge encoded in our causal graphs. This will help us check our assumptions, update our knowledge, and choose between several possible hypotheses for how the world works.